Hello everyone, my name is Tanya Garg and today we will be discussing about methods to compute LCM and HCF of 8-bit integers using assembly language programming. So first we will discuss what LCM is. LCM is the least common multiple of a set of integers a1, a2 till an, and it is basically the smallest integer which is divisible by all the integers in the given set. For example, if you want to determine the LCM of 3 and 5, we'll first list out the multiples of them. So multiples of 3 are 3, 6, 9, 12, 15, 18, 21, 24, and so on. And multiples of 5 are 5, 10, 15, 20, 25, so on. So it is evident from the list given over here that the smallest integer, which is the common multiple of both 3 and 5, is 15. So the LCM of 3 and 5 is 15. Next, we will discuss what is HCF. HCF, or the highest common factor of a set of integers a1, a2, a3 till an, is the largest integer which divides all those integers. So, for example, if you have to find the HCF of 30 and 42, we'll first list out their factors. So, the factors of 30 are 1, 2, 3, 5, 6, 10, 15, 30, and the factors of 42 are 1, 2, 3, 6, 7, 14, 21, and 42. It is evident that the largest integer, which is a common factor of both 30 and 42, is 6. So the HCF of 30 and 42 is 6. While making an assembly language program, we should keep some steps in mind. The first step should always be to make an algorithm or a flowchart which gives the proper blueprint of what we're going to do. Then, according to that algorithm, we should make our assembly language program either on the 8085 microprocessor, or we could use a simulator like we'll be using today. And then we can even calculate the number of cycles which are run in the algorithm to calculate the delay that our code introduces to the system of code. In today's video, we'll be discussing the flowchart, algorithms, and the ALP code of one unique method to calculate the HCF of 2 and more than 2 number of integers, and two unique methods to calculate the LCM of 2 and more than 2 number of integers. So first we'll discuss that how can we compute the HCF of 8-bit integers. To calculate the HCF of 8-bit integers, we'll be basically using the Euclidean algorithm, and we'll be using a concept that says that if we have to calculate the HCF of two numbers and we subtract the smaller number from the larger number, the HCF remains unchanged. So the algorithm for that is as follows: that first we'll input the two numbers and store them, and then we'll compare them. If both of them are equal, then the HCF is the number itself, because the highest common factor of a number is the number itself. Then if the numbers are not equal, then we'll store the greater number in the accumulator. As discussed right now, that we have to know which one is the larger number and smaller number, because we have to subtract the smaller number from the larger number. So we'll first find out which one is the bigger number and store it in the accumulator, and then we'll subtract b, which has the smaller number, from a, which has a greater number, and then compare the updated values. So basically we'll be comparing b and a minus b, and we keep on repeating this process. That is, we keep on subtracting the updated smaller values from the updated large values till both of them are equal. So we have basically 2 points. First is that subtracting the smaller from the larger number does not change the HCF of a set of numbers, and second, that if both the numbers are equal, then the HCF is the number itself. By using these 2 points, we'll calculate the HCF of two integers. So here is the flowchart of the algorithm. First, we'll input the first integer, then we'll store it in B, and then we'll input the second integer. By default, when we're using the IO ports, the integer is stored in the accumulator. Then we'll check if both of them are equal. If both of them are equal, then we'll put it in the IO port as an output, and then terminate the program. We're doing this because if both the numbers are equal, then the number itself is the HCF. But what if they're not equal? If they're not equal, first of all, we'll find out which one is the bigger number, and then store the bigger number in the accumulator. And after that, we subtract the smaller number, which is b in our case, from a, which is the larger number, and compare the new updated values. After comparing the new updated values, again, if both of them are equal, the number itself is the HCF. If not, we again check which is the greater number, store it in the accumulator, subtract it, and the loop goes on and on till both the numbers become equal. Now we'll discuss a simulator code. This is the GNU simulator code for the first branch that we discussed. This branch is essentially the input-output branch. And over here, first we'll input the first integer from the 00 IO port, and then we'll put this integer in the B register. We're doing move b comma a over here because a is the source and b is the destination. So the number goes from a to b. Then we'll input the second integer from the 01 IO port and then compare the two values. CMP-B is basically that we calculate A minus B and then we check what the number is. So if the number is 0, that means that A and B were equal. So JZOP means that jump to OP if 0. OP is nothing but the output subsection of our code, and if both of them are equal, that is A is equal to B, we output that number itself, because as discussed, the number itself is the HCF. So in OP, we have that it outputs to the 0 to IO port, and then we terminate the program. This is the GNU code for the second branch. So what if A is not equal to B? If A is not equal to B, then we check that which one out of A and B is greater. And we store the greater value in the accumulator by swapping the two numbers. So how do we swap them now? We use a temporary or another register. Basically, like over here, we're using the C register and we're storing the values accordingly to swap our values in A and B. And this process, now what is this rec and what is JNC? JNC is basically jump if not carry to the recursive subsection. Jump if not carry is only possible if A is greater than B. The recursive subsection that we have over here, the first step is subtract B. Subtract B means that subtract B from A. A is always the default value that we're using. So this is basically this point over here, and then we have to compare the values again, like over here. If both of them are equal, then we go to the output subsection again. If they are not equal, then we have to check which one is greater, put the greater number in the accumulator, and then we have to run the recursive subsection again and again till both of them become equal. So now we'll be discussing the GNU code for this particular algorithm, and we'll see it running now. So this is basically the GNU code for to compute the HCF of two 8-bit numbers, and this code is exactly what we just discussed along with the flowcharts in our presentation. The first integer that we'll be taking is 4 and the second is 24, as we can see in the IO ports. So if I run this program, we'll see that in the second IO port we get the HCF value of 4 and 24, which is 4. So by using this, one can calculate the HCF of two 8-bit numbers. This code is present in the GitHub link that has been shared along with the video. Next, we will discuss that how can we find the HCF of n integers. So it's nothing, it's just 90% similar to what we just discussed, that how can we calculate the HCF of two integers. So to calculate the HCF of n integers, first step is to basically take two integers as an input and then calculating their HCF by the method that we just discussed, then storing this HCF somewhere and inputting a third integer. Then we'll take the HCF of this third inputted integer and the previously calculated HCF. This HCF would be the HCF of three integers. So these steps are repeated till all the n integers are used up. So basically we're calculating HCF here n minus 1 number of times, because for 2 it takes 1, 3 it takes 2, because we'll be calling the HCF subroutine n minus 1 number of times. So say if HCF 1 is the HCF of integer 1 and 2, so HCF2, which will be the HCF of integer 1, integer 2 and integer 3, that would be equal to the HCF of integer 3 and the HCF 1. Now we will discuss the flowchart. The flowchart is exactly same as what we discussed in the previous example. Only difference we have over here is we have to take 3 inputs at a time. So in this example, we have taken n equals to 3. This can be generalized for any n, but in this example, it's n equals to 3. Then we have the HCF subroutine over here. The HCF subroutine is what we discussed in the previous example. In the HCF subroutine, the only difference is that in the previous program, we were terminating a program after the HCF was calculated, but instead over here we're returning the control to the original routine. So basically after coming to this point, it goes to the HCF subroutine, and after computing the HCF, it goes back to this point and it continues from here. So this is the only difference that is there in this flowchart or in this algorithm and in the previous algorithm that we discussed. So this is the GNU code for this algorithm. This is the input branch that we have, and first we'll take the first integer as the input, move it to B, then take the second integer as the input, and then call the HCF subroutine. We have an HCF subroutine, and then we're calling it by using the call mnemonic, and then we're storing this into the B register. Then we're calling the third integer calling the HCF subroutine again to calculate the HCF of all three integers together, and then we are terminating the program. Now we have the HCF subroutine, which is the same as what we discussed earlier. Um, Here we are comparing B with A, and then if both of them are equal, then that number itself is the HCF, and then we're outputting that number only. If it's not equal, then we check which is the greater number and store it in the accumulator, and then subtract the smaller number from the greater number, and then store it in the accumulator again, and check if both of them were equal. If they are equal, then the number itself is the HCF. If not, then the steps are repeated again and again. So now we'll see an example for to calculate the HCF of three integers in the GNU simulator. So here is the code of calculating HCF of three 8-bit numbers. This one is the main routine that we discussed, which is the input and output routine, and where we are calling HCF twice. So it's a three 8-bit numbers. So we'll be calling HCF twice over here and over here. So the HCF subroutine, this one, is what it was in the two 8-bit number example. And the numbers that we will be using in this example are 4, 24, and 18. The output of all these HCF should be in the 0, 3 IO port. So after running this code, we'll get the answer as 2, which is the HCF of 4, 24, and 18, because the highest common factor of all these numbers is 2. So one can even generalize this code to make it for an n 8-bit numbers. You'll just have to call HCF more number of times, and take into account that we have to take more inputs because we want n numbers this time instead of 3. After discussing the HCF, we'll be discussing that how can we compute the LCM of 8-bit integers. First, we will discuss the algorithm to compute the LCM of two integers. So the algorithm is as follows. First, we'll take the two integers as an input and store them in registers, and then we'll subtract B from A. So basically subtract one number from the other number, and we'll keep on subtracting it till A becomes negative. When A becomes negative, then we'll add B to A once. So after all these steps, what we have with us is actually A modulus B, the remainder after dividing A by B. So if this modulus is equal to 0, that is if the remainder is 0, then A is a multiple of B. And if A is a multiple of B, and obviously A is a multiple of itself, then A is actually the LCM of A and B. And then we would return that as the LCM. But what if the modulus is not equal to 0? If the modulus is not equal to 0, then we take the modulus of 2A and B. So we'll do 2A modulus B. And then this process keeps on repeating. So basically over here, we are storing the original value of A in D and in C. And if A is not equal to 0, which is basically if A modulo B is not equal to 0, then we would add these two values and we'll have 2A. And after having 2A, we'll repeat these steps again. That will subtract B from 2A again and again and get 2A modulus B. And if that is not equal to 0, then we'll do it for 3A. And the process keeps on going on till we find a multiple of A which is divisible by B. When we find a multiple of A which is divisible by B, that multiple of A is the LCM of A and B. So now we'll be discussing the flowchart. This is the input-output branch. We're taking the first integer as an input and storing it in C and D. We're taking multiple copies over here because after calculating A modulo B, we still need the original value of A to calculate 2A and 3A and 4A and so on. So we need to store it in separate registers to retain those values and keep them untouched. Then we have to input the second integer from the IO port, and we'll store that in B, and then we'll store the value of C in A. So basically our registers A, C, and D have the value of integer 1, and the register B have the value of integer 2. So this branch is basically the main LCM branch. Over here what we're doing is subtracting B from A, and then if A is greater than 0, we're calculating this again and again till A becomes less than 0. And once A is less than 0, we add B to A once. So after computing all these, we're essentially getting A modulus B. Then we check if A modulus B is equal to 0. If it is equal to 0, then we'll output the original value of A, which is stored in D, as the LCM of A comma B. Because if A modulus B is equal to 0, then A is a multiple of B. But if it's not true, then what we're doing is we're adding 1A to the original value of A. So basically A becomes 2A this time, and the next time 2A will become 3A because we're adding A once to the present value of A. So then if it's not equal to 0, then all these processes are repeated again, and we are essentially calculating 2a modulus b. And if 2a modulus b is not equal to 0, then we'll calculate 3a modulus b. And then the process continues till we find the LCM of a comma b. Now we'll discuss the GNU simulator code. So this is basically the input-output branch, and first we'll input the first integer from the IO port. Then we'll move the values to C and D, because as discussed, we want to retain the values for some time because we'll be using it again later on. Then we're inputting the second value and storing it in the respective registers again. Then we have the main LCM branch. So we're subtracting b from a over here. Sub b means a becomes a minus b. And then if not carry, then we have to jump to rec again. So not carry would mean that a is greater than 0. We will have a carry only when a becomes negative. If a is positive, we will not have a carry, and then we will jump back to this loop and subtract b again from a. If a becomes negative, we'll add b once and compare it to 0. Now a holds the value of a modulus b. If it is equal to 0, then a is the LCM, and then we would go to the output subsection and we'll output the value of a in the 0 to IO port. But if it's not equal to 0, then we would move the value of 2a to the accumulator. And once the accumulator has a value of 2a, we jump back to the recursive subsection and do the process again to calculate 2a modulus b. Now we'll see the GNU simulator code running for some particular example. So this is the GNU simulator, and this is exactly the code that we just discussed along with the flowcharts. The first integer that we will be using is 4, and the second integer that we will be using is 5. So basically we'll be calculating the LCM of 5. The expected value is 20, as we know from our normal algebra. So if we run this program, the value in the second IO port is 20 as expected, which is basically the LCM of 5 and 4. So we can compute the LCM of two 8-bit numbers by using this particular code in the GNU simulator. This code can also be found in the GitHub link that is provided along with the video. Now we will discuss that how can we compute the LCM of n integers. This is the same method as how we extended the HCF of 2 integers to HCF of n integers. Now we'll extend the LCM of 2 integers to LCM of n integers. It's exactly the same. First, we will take the LCM of 2 integers, and then we would take the LCM of the third integer along with the LCM that was just calculated. So LCM 2 is basically LCM of the third integer along and LCM 1. So if we have 1, 2, 3, then we'll first take the LCM of 1 and 2, and whatever the value is, we'll take the LCM of that with 3, and we'll get the LCM of all the 3 numbers together. So this is the algorithm for that. Now we will discuss the flowchart. This in the beginning might look a bit daunting, but it's just the inputs we're taking and storing it in different registers. This is a larger function because we have to store it in different registers as discussed before, because we want to retain some original values because they will be used later on. And this LCM subroutine that has been called twice over here, it's exactly the same as what we discussed in the 2 integer example. Similar to the previous examples, this flowchart is for n equals to 3. This can be generalized for any value of n, but over here we're talking about n equals to 3 only. So we'll discuss the GNU simulator code now. The GNU simulator code for this input branch is basically that we'll first take the input from the 0, 0 IO port, and then we'll shift the values in the respective registers in which we want the values to be, and then we'll take the second input of the integer 2, and then we'll call the LCM subroutine. So we're using the call mnemonic again, and we're calling the LCM subroutine, and then we're calling we've stored this LCM in the 0, 3 IO port, and then we're inputting the third integer from the IO port, from the 0 to IO port, and then storing it in the respective registers again. Then we're inputting the LCM again and then storing it in the respective registers, and then we're calling the LCM subroutine again, and then we're terminating the program. This LCM subroutine is exactly the same as what was discussed in the 2 integer example. So basically, we're subtracting b from a as long as a is positive. When a becomes negative, we add b to it, and that gives us a modulus b. And then we compare it to 0. If it is equal to 0, then a is the LCM. If it is not equal to 0, we check for 2a modulus b, and then so on. Like it becomes 3a modulus b, 4a modulus b, and so on, till the value in the accumulator modulus b becomes 0. If it becomes 0, then we would output it in the fourth IO port, or basically the 03 IO port, and then we would return the control to the original routine. So instead of terminating the program, we're returning the control to the original routine. So now we will discuss and see how we can run this in the GNU simulator with an example. So this is basically the GNU simulator, and this is the code that we just discussed along with the flowcharts to compute the LCM of three 8-bit numbers. So the numbers that we'll be taking are 4, 5, and 9, as can be seen in the IO ports. And this is basically the input routine, the main routine in which we're calling the LCM and we're taking the inputs. And this is the LCM subroutine, which is similar to what we used in the 2-number example. So if we run this program, we'll get the LCM as 180 in the 03 IO port, which is as expected. The LCM of 4, 5, and 9 is 180 because they don't have any common factors, so it will just be the multiplication of 4, 5, and 9. So by doing this, one can even make a generalized n 8-bit number LCM program. We just will have to call the LCM subroutine n minus 1 number of times. Like over here, we had used 3 integers and we'd call it twice. So one can even generalize it for any number of n. As said earlier, we'll be discussing two unique methods to calculate the LCM of 8-bit integers. We've discussed the first method just now. The second method is by using the HCF. So if you're doing some computations in a high-level programming language like Python or Java, the formula that you would mostly be using to calculate the LCM is the product of all those integers divided by the HCF of those integers. So now we'll be computing the LCM of n-bit integers by using this particular formula discussed here. This formula is valid for any number of n, but over here we'll be discussing it only for n equals to 2. So this formula involves three functions. One is product, or basically multiplication of all the integers given in the set. Second is HCF of all the numbers, and third is the division of the product and the HCF. So first step is multiplication of the two numbers. So over here we're taking n is equal to 2. So the first step is multiplication of the two numbers. Multiplication, we'll be using the very basic concept of multiple addition. Multiplication is nothing but repeated addition. Say if you have to calculate a into b, we just have to add b a number of times. So that's exactly what we're doing over here. First, we take the two numbers as an input and then store them in registers, and we initialize a equals to 0. We add b to the accumulator c number of times, where c is the other number of which we want to take the product of. And if a is greater than 255, or basically the largest value that an accumulator can store because it's an 8-bit accumulator, then we would increment d. So d would basically hold the most significant bits of the product, and a would hold the least significant bits of the product. So this process would continue till c becomes 0, or basically we've added b adequate number of amount of times. Then the second step is to calculate the HCF. We will calculate the HCF by using the same method that we used or discussed while computing the HCF of two 8-bit integers. Then the next is division. Over here, you have to divide a 16-bit number by an 8-bit number, because multiplication of a big 8-bit number, say FF with itself, say FF into FF is a 16-bit number. So we need to take into consideration the D, or the most significant bits also. So division is basically repeated subtraction. Multiplication was repeated addition. Division is repeated subtraction. So we know that the product and the HCF of a given set of numbers will not have a remainder. It will only have a quotient. Remainder will be equal to 0 in this case. So we only have to subtract the denominator from the numerator some number of times, the quotient number of times, to make the numerator 0. So that's exactly what we'll be doing over here. We will load the value of the product and the HCF from the memory, and then we will subtract C from A. C is basically the denominator and A is the numerator. And and with each subtraction we will increase the value of HL by 1. So HL is basically initialized to 0 as of now, and if we increase it to 1, we will increasing the number of divisions that have taken place, or basically at the end of the computation we will have the quotient of our division in HL. So till HL, till A is greater than 0, we will be incrementing HL. If A becomes less than 0, that means that the least significant bits have become 0, but we still have the most significant bits with us. So we have to repeat it again for by taking into consideration the most significant bits also. So we keep on repeating the subtraction process again and again till we have B equal to 0. So B has the most significant bits at the time. So when both the most significant bits and the least significant bits become 0, then HL will have the value of the quotient of the division of the product and the HCF. So this is basically the flowchart of the algorithm that we just discussed. We basically have the three main steps in our main routine. The first is multiplication, then calculating the HCF, then division. Multiplication, as discussed, is multiple addition or repeated addition. So over here, first we're taking the first integer as an input, storing it in B, then taking the second integer as an input and storing the value of A in C. And then we're keeping the value of A equals to 0. Then we're basically adding B again and again to A till C becomes 0, or till we've added B adequate number of times. In the middle, if D is incremented by 1 if carry is equal to 1. Carry becomes equal to 1 when A exceeds the value of FF, or the highest number that an accumulator can hold. So when that happens, then we have to increase D by 1, or basically the most significant digits increase by 1 at that time. So after repeated addition, we store the value of A and D in the memory. Then we have to calculate the HCF. After multiplication is the HCF. So to calculate the HCF, we use the exactly same method that was discussed before. This is the input branch, and this is the repeating recursion branch. Then we have division, and then in division what happens is we take three inputs. One is the most significant bits of the product, second is the least significant bits of the product, and third are the HCF values. And after taking the inputs, we're setting HL to 0, and then we're subtracting C from A repeatedly. B over here holds the most significant bits. So first we will subtract the HCF value from the least significant bits only. Once the least significant bits become 0 or less than 0, then we would decrease the most significant bits by 1, and then the process continues again and again till both the most significant bits and the least significant bits become 0. So after that happens, then we have the quotient of our division of the product and the HCF in HL pair, and then we would output that HL pair through the IO ports and then return to the main routine, after which, after division, we terminate the program. So now we will see the GNU code. So in the main routine, we only have the three call functions that terminate. First we'll call the multiplication subroutine, then the HCF subroutine, and then the division subroutine, and then we'll terminate the program. In the multiplication subroutine, first we'll take the inputs and first we'll take both the inputs, the first integer and the second integer, and then store them in the respective registers. And then we have the repeated addition. So we're adding B to a 0 initialized accumulator, and if we have a carry, then we increment D. If we don't have a carry, then this particular condition, that jump to next if not carry, this becomes true and we directly jump to next. If this wasn't true, then we would increment D first and then come to next. In next, what happens is we decrement C once. Decrement C is basically we are taking into account how many additions have been done. So by decreasing C, we are saying that okay, one addition has been done. So after decreasing C, we check if the value of C is 0 or not. If the value of C is 0, that means that the adequate amount of additions have been done, and then we go to the storing step. So basically we'll be storing the values of A and D in the memory. If it's not equal to 0, then the repeated addition continues till C becomes equal to 0. Then we have the HCF subroutine, as was discussed earlier. So we're taking the inputs, and then if both the numbers are originally equal, then the number itself is the HCF. Otherwise, we check which is the greater number stored in the accumulator, subtract the smaller number from the larger number, and then check again if it's equal or not. And this process is continued till both of them become equal. Then we have the division subroutine. In the division subroutine, we basically have repeated subtraction as was discussed earlier. First, we take all the inputs from the memory. We have stored our product and HCF in the memory as of now. So we're taking all the inputs from the memory, and then we're subtracting C from A. Now, if C becomes negative, then we'll be decreasing B. We'll be decreasing B because now the least significant bits or all the A has become 0. So now we have to take into consideration the most significant bits too, and that's why we are decreasing B, which has the most significant bits. And then if even B becomes 0, then we will go to the output subsection, because if the most significant bits also become 0, then our entire numerator has become 0 and the division has gotten over. So when B also becomes 0, that is jump to store. If B is equal to 0, then we'll go on to storing those values or outputting those values through the IO port. If it's not equal to 0, then we are going to increment our HL by 1. Incrementing HL by 1 means that one division has successfully taken place, and then go on to the loop 1, which is again the repeated subtraction process. So by this we can find the quotient, or basically divide a 16-bit number by an 8-bit number. Now we will see that how does this code look in the GNU simulator and run with an example. So here we have the code that we just discussed along with the flowcharts. This is the main routine that we have. This first we're calling the multiplication and the HCF and the division subroutine. This is the multiplication subroutine as discussed right now along with the flowchart. This is the HCF subroutine that was discussed in the previous examples when we calculated only the HCF of two numbers, and then this is the division subroutine that was just discussed along with the flowchart. So the two numbers that we're taking over here are 5 and 4. So if I run this code, then we can see that the 0 to IO port has the value of 20, which is the LCM of 4 and 5. Now the formula that we used was product of 4 and 5 upon HCF of 4 and 5. So the product of 4 and 5 is 20 and HCF of 4 and 5 is 1, because they do not have any factor other than 1 which is common for both 4 and 5. So let's take another example. Let's take the two numbers as 40 and 5. So if I run this program, then our LCM comes out to be 40, which is product of 40 and 5, which gives us 200, divided by the HCF of 40 and 5, which is 5. The highest common factor of 40 and 5 is 5. So it's 200 by 5, which gives us 40. So by this we can see that we can calculate the LCM of two 8-bit numbers by using the product and HCF formula. So thank you.